During this webinar, we'll be using some TI tools for solving problems that involve Unit 3 subject matter. Obviously, we can't cover everything, but we wanted to look at a few little things that the calculator is very handy for. In particular, parametric equations, which seem to be not used much with the calculator. And I wanted to look at using math boxes too. So these are quite handy for doing quick calculations and reviewing all your notes throughout the exam. Also, you should have familiarity with the formula sheet. You don't have to know the formulas off by heart, but you should know how to use them. So obviously, there's a handout with the questions on them. So they're divided up into simple familiar, complex familiar, and complex unfamiliar. I'm just going to be using the TI calculator to go through questions and answers. So the tools we'll be looking at today in that orange box are the calculator, adding a calculator and adding a graph, and the notes page. So this is a very helpful tool. So you can add a notes page by clicking on Insert, and you'll see their notes page is in yellow. So I'm actually in the notes page now. And one of the things I wanted to push was using a math box. So to do a math box, if we hit Control and M, the math box will come up, and within that math box you'll have, you can click on the menu and you can click on Calculations, and you'll have access to all the tools that you need. It's also very handy if you know the tools, the names of the tools that you'll be using off by heart. So I would suggest after an exam starts, if you wrote down on the formula sheet some tool names. So I'll go through some of these now. So most of the tools we'll be using today can be found in the menu or in the equation or the template, the little red template there. So you can see there's summation tools and product tools. Next to that we have matrix tools. We can enter a matrix, the derivative, etc. The absolute value function is also there. And we'll go to the first problem. So this could be sets of planes. So we could have 3 equations of a plane, or could just be 3 simultaneous equations. The question might ask you to solve using algebra or using matrix algebra with inverses, but you could actually do this using row reduction. So you might have to show all the working, and that's where we can use augmented matrices and Gaussian elimination, where you add rows or multiply rows by constants and swap them all around. But there is a nice little tool that, if you can remember it, you can look it up in the menu for the toolbox, but if you remember RREF, that's the row reduction echelon form of matrices. So what we need to do first of all is rearrange the equation so we can get it with all the variables on the left-hand side and the constants on the right-hand side. And then I've got the tool set up there already. I'll just show you how to do that. So if we go insert a math box, Control and M for math box, and then because I know that the tool is RREF, make sure when you're using these tools too that you always use a bracket, and then we can put in the matrix. So if we go to our template there, click on that, and it's a 3 by 4. So we enter all those values. So I've already got it done down below, so I won't waste time in doing all that. Just make sure when you're using the math box, you're inside the math box. So at the moment, I'm outside the math box. When you click inside, you'll see this red dotted line. And when you push enter, you'll see the answers for that are 2, x is 2, y is -3, and z is 4. So this could be 3 lines intersecting at a point, or it could be 3 planes intersecting at a point. So very important using the math box, and you can use that tool RREF. You can also find it in the menu, if you're inside a math box, I'll just do that again. So if you click on menu, calculations, and then if you go down to down here, got matrix vectors, and then down below here, vector. So you can see it's in there, and it's in there somewhere. But anyway, we'll get back to that. So I'll just undo that and go on to the next page. Now, the next question is using the Leslie matrix model, and this represents a population of rats over a lifespan of 3 years. So we've got the birth rate. This could be for the young, 1.2 per rat, and then 2.1 for the juveniles, and then the older rats don't have any offspring. And then we've got the survival rate, 0.4 and 0.2 here. And our initial matrix is P0, so we've got 10 in each year level there. So the question is finding what's a suitable harvesting factor or culling factor. So after a 3-year period, how many rats can we take out of the population so that we have a population that ends up being stable? So we can define these matrices again. Once again, it's best to define the matrix using a variable. So I'll just do another example how we do that. I'll get some space here. So if I wanted to define, say, another matrix, because I've already got these set up, if I had P, and then this is very important too, if you hit Control and the template, so now we're going to assign a matrix, and if we click on the template there, I'll just do a smaller matrix. So this is not the Leslie matrix, this is just an example. And if I put in, now I don't want to use P actually because I'm using P further down. So let's say we use K, that might be better. And now don't jump out of the box, hit enter, and there's our matrix there. So matrix K, whenever I click K, that should turn up when I have it inside a math box. So sorry, get that again. Sorry, I'm not doing something right there. We'll skip that. We'll go down to our matrices are defined here already. So we've got L and P, and this is a matrix, a row matrix of 1, so we can add up the total. So let's look at some values of N. So I've done some here. If we type in E times L to the 5th times P, so this is after 15 years, there'll be 238 female rats altogether. After 7 time intervals or 21 years, there'll be 686 rats. And eventually, after 8 time intervals, we get to 1,000 rats, or 1,163. Now, we can look at the ratio of Control M, get my maths box. I'm just going to put in a fraction template here. And so if I look at, say, the 9th time period of 11973, I won't worry about the decimal, over the period just before that, 1163 and 1164, and hit enter, you can see that that didn't have a decimal in there. Put a decimal in there. You can see that approaches 1.695. So looking at other values, over the page, looking at other values, we've got any of these ratios. If if you did the 20th generation 656660 divided by 387308, it would approach 1.695. So the culling factor will be 1 minus 1 over 1.695. So we need to cull 41% of the population every 3 years, and then the population should remain stable. Okay. The next question was looking at use of complex numbers in the determinant of a matrix. Now, I'll just go to the next page quickly. The formula sheet does have, I know students can be stressed out during exams, but it does have the determinant in there of a 2 by 2, not a 3 by 3. So you can actually wing it, I guess, and get the determinant here. The non-CAS calculator won't give you the variables, so you'll have to work this out yourself. So if we go x by the determinant of 2141 and minus y, we could go across the row as well, minus the determinant of negative 5i, 2 and 4i, etc., plus 2 by that. So we end up with this expression. And collecting all the real and imaginary bits, so we end up with negative 5y minus 8 is the real bit, and then negative 2x plus 8y minus 10 is the imaginary bit. So we end up with two simultaneous equations, negative 5y minus 8 equals 2, and negative 2x plus 8y minus 10 equals 4. Now we can solve them simultaneously. We can use the calculator to check. We could use Linsolve, or you could use Matrices. And so that's the formula sheet again. So over here, I've worked out what Linsolve is, and you can see we end up with x is negative 15 and y equals negative 2. Now, when you put this in, you can check with a calculator page. I'm in a calculator page. These pages alternate, so we've got a grey area and a white area. So in the calculator page, have to be careful that you don't use the absolute value symbol. You have to use the determinant. You have to type in determinant, or it's probably easiest to type in determinant. So I'll just show you what happens if you use the absolute value symbol. If we use that and put in a matrix, I'll just use a 2 by 2. So if we put in negative 2, so it won't, it'll just take the absolute value of negative 2. It won't actually do anything. So you need to type in depth for determinant. Don't forget to use an open bracket. And then if I put this in, I'm just going to copy that, paste that in there, and then hit enter. So it should be negative 2 by 3, negative 6 minus 3, so it should give you negative 9. So just remember, when doing the determinant, if you type in DET, you won't have any issues with the matrices. Okay, so that's the end of those 3 problems. We'll now go on to the vectors. And in the formula sheet, there's a number of different formulae. So the angle between 2 vectors, the scalar dot product, the vector equation of a line, the Cartesian form, vector cross product, etc. So all these are in the formula sheet, and it's handy if you know what tools in the calculator are associated with the formula sheet. Just remember the absolute value of A by absolute value of B. You need to enter that as a matrix. I'll show you that in a second, or you can use the command norm. Okay, so just as an aside, if we rearrange the formula there, so we can, I've got as a note, don't use the absolute value. You need to use the norm of A and the norm of B. And the dot product, you can find all these commands in the menu, but if you can remember them, dot P and norm A, etc. And the cross product, so is cross P open bracket. So they're handy to remember, but you can find them in the menu or in the book. Okay, so here's question 4. It says determine the area of the triangle PQR with vertices P1, 5, -2, etc. Now the diagram wasn't there, so basically when you're solving these problems, we want a vector going from the heads at Q, sorry, the tails at Q and the heads at P, and then we want the tail at Q and the head at R. So you could do it at different spots, so it doesn't matter where you pick as long as you have the head running away from the point Q. Okay, so I've defined these vectors P, Q, and R, and I've just used a notes page again. You can use the formula sheet. So the formula sheet, if we just go back to the formula sheet, you can see on the formula sheet it does have the vector cross product there. So if we have forgotten everything, so we can use the two vectors, and A2B3 minus A3B2 is the I coefficient. The next one's the J, and the next one is the K. So if we use the formula sheet, we should end up with -9I minus 13J minus 6K. Now, the area of the triangle is half the magnitude of the cross product. So because I've got, I know I can just use this. Yeah, I'll just insert a math box. So if I put in Control M, so 0.5 times the norm, and you'll notice it jumps up from italic to non-italic, and then always use an open bracket, and then put in our matrix form. So we want a row with 3 entries. You could go down as well. So we'll put in 9, -13, and -6, and it should, remember, don't jump outside the box, you have to be inside the box, so you have that red dotted rectangle around it. Hit enter, so that should be the area of the rectangle. Now, the other way of doing the cross product, we could get that vector as well if we don't use our formula sheet. So because we've defined our vectors P, Q, and R, remember we want a vector going with the head at P and the tail at Q, and the head at R and the tail at Q. So we can define our vectors. I'll just type it in again here. So I'm using a math box. You could do this on a calculator page too. Cross product. So the first vector from Q to R, we have to go, sorry, from Q to P, we go P, take Q, comma, and then R, take Q, and hit enter, and we should get that. And if we wanted to, we could put in there norm. Might as well do that. Norm, open brackets. I'm just going to copy that again. And hit enter. And it should give that, which is twice the area. I didn't put in the 0.5, so that's the area of the parallelogram, but we need to put in 0.5 for the area of the triangle. Okay. Next question. So this time we want to find the Cartesian equation of the plane and sketch a graph of the plane. So once again, I've defined the 3 points, A, B, and C. So remember to define a point. So I wanted to do a point D, because I've defined these already. I need to put in that column there, and then I can put in, using the equation template, I'll put in a vector, another vector. Okay, so there's my other vector. Okay. Now, so I've got A, B, and C defined. And here's my cross product. So I'm calling it N. And I've defined it as B take A. So that's the vector going from the tail at A going to B and the tail at A going to C. So this vector will be at right angles to the plane. And I'm just going to use the point A. So for that, we can use the dot product because we've defined A on the previous page and we've got N defined. So the dot product, dot P, A comma N ends up being -4. And then we can rearrange that equation. So we get negative x minus 2y minus 2z equals -4. Rearrange that. So we then get z equals 4 take x minus 2y. And we can graph that. So the last part of the question was to graph that. So if you go into menu, view 3D, and if you put the point in, so I won't actually do that because I'm running out of time, but you can type in the equation there. Okay. And it's a bit hard to sketch that because it's 3D. Just wanted to get on to the last question before I hand over to Jim. So this is a soccer ball being kicked from a starting height of 1 metre at a speed of 25 metres per second. The angle is 45 degrees with respect to the ground. Find the maximum height reached by the soccer ball and the time at which this occurs. Will the ball clear a 4 metre high fence located 60 metres away from when it was kicked? So if we write this in component form, so we've got 25, I've done it as in red for the X component and blue for the Y component. So 25 by cos pi on t 4i, and then 25 sine pi on t, pi on 4t minus a half at squared plus 1 because it's 1 metre above the ground. And then I've defined a function for this y component because we want to look at that as well. So to define a function, I've done that in terms of x. So we're looking at a graph of that. But I wanted to show you what you can do with parametric equations. So if we go to a new page and enter in, I've already entered this in, but we would go to, show you quickly, a graphs page and menu, and then graph edit. And we'd want parametric, so we have to put these in terms of the x and y and using t. So I'll just show you what that looks like. So there's the path of the soccer ball. I've done a zoom fit. And if you click on menu and trace, down here in the bottom, you can see the coordinates. So you can actually follow the path of the ball, and you can see at about 1.8 seconds, it's at the maximum height of 16.9 metres. So very handy, the parametric equation, so you can see what's happening, and you can work out also at a distance of 60.1 metres, the height of the ball is 4.46 metres. So it has actually cleared the fence by 60 centimetres at a time of 3.4 seconds. So you can actually use all that information. So you'd have to show working and everything. So using the horizontal component, we've got 60 equals 25 cos pi t on 4. So at what time does it get to 60 metres away? We can use our linear solve or n solve that equation. You can write the variables in terms of t or x. So it's about 3.39 seconds, which we saw back here. It was 3.4 seconds, so that's been rounded. And the derivative, the y component, I have that defined, and I've put in 3.39, and that also gives So that's the height at 3.39 seconds. So you can also use the what was the time? So just go back one. And I think it was 16.8. The time was 3.4, I think, but anyway. No, that wasn't it. Okay, now I'm going to hand over to Jim now, and Jim's going to look at solving some complex number problems, and I'll hand it to Jim. Thank you for listening.
Okay, thank you, Stephen. Hopefully you can all share my screen, which is just a blank calculator page at the moment, and I'm going to have a look at a few complex number questions. Now, just in starting, I might quickly reiterate and mention that if you're in a calculator page, menu, numbers, complex number tools, and all of those basic calculation requirements that you have for complex numbers can be done there. So if you aren't familiar with the calculator and you need to look at those, go back and check on the website. We addressed those in some of the webinars that we did at the end of term 1. So if you have a look at those. For today, focusing on exams, we're going to have a look at some of the more involved problems, complex unfamiliar and complex familiar. So going to take them perhaps in the wrong order, in a sense that I'm going to start with the complex unfamiliar, supposedly the harder ones, and then look at a few complex familiar ones, just in case we run out of time. We thought there might be value in looking at something a little bit different or unusual and get you used to doing that sort of thing. When you get to these sort of problems, then you need to realise that it's highly unlikely that any of these complex problems are going to be solved by just typing something into the calculator and pressing a button. You're going to have to do some work and then make the calculator useful for you at the appropriate point. So we've got this problem here. We're looking for an integral value of n such that the complex number √3 plus I to the power n intersects with an ellipse defined by that equation that's shown on screen. Now, a couple of little hints and tips here. As soon as you see anything to do with complex numbers, and particularly powers of complex numbers, then you should immediately be thinking de Moivre's theorem. And if you're thinking de Moivre's theorem, then it works in the form when you've got the number in the form mod argument form, r cis theta. So there's a starting point to this problem. Immediately it tells you that you need to get that into mod argument form and then apply de Moivre's theorem and see what you can do with it. And Stephen gave you a little hint there before that we can use the parametric equation grapher to graph the two parts of that complex number, the real part and the imaginary part, and hence get a representation. So let's have a quick look at that. So parametric equations, but the first thing is to get that in mod argument form. Again, you have tools on your calculator that will do that, but we've just worked it through there. Stephen's already alluded to the use of the formula sheet, but that's pretty straightforward. So we get it in this form, and for this example, we've left it in degrees. So need to make sure that your document is set to operate in degrees. But our complex number Z is now 2 to the power n cos 30 times n and I sine 30 times n. So having got that, we now put it into the parametric grapher. So it goes into that form. The x component, or the x part of the parametric, is the real part, and this is the imaginary part. Go to the graphs page and insert that in there. And we've got fairly detailed instructions there for you. So, and also add the ellipse. So go to the equation template, select ellipse, and then click on menu and so on, just like you saw Stephen do earlier. So let's have a look. We've done all this, set it up so that you don't have to just watch me type. And there's the graph. So there's the ellipse that we've got in there. There's the equation, and there's the parametric equation. And as we did before, we're going to go to graph trace and make our way through that trace, and you can see down here the values on the screen. You can use trace. You might also recognize that they're going to intersect up here. We're looking for integer values, and so we could make a big assumption there that they're going to intersect on the axis there at that point, but we will just take the trace through and see what's happening there, and see that in fact it does in fact intersect there where t is equal to 3. Well, that's the syntax of the calculator. In our original equation, that was the index of our complex number z to the power n. And so our answer to that problem is that the graph intersects the ellipse when n is 3. Let's look at this one. If z is equal to x plus 3i and z2 is 3 minus 2i, determine possible values of x. Determine possible values of this thing in here, given that the modulus of z1 over z2 is equal to 1. And it's a complex familiar because you would have done quite a lot of manipulation of these complex numbers in there. Thought we'd throw one in just to remind you of a few things, so that if you are dividing a complex number, then we do that by multiplying by the complex conjugate, and so that we get rid of the complex number on the bottom, and we end up with that expression there. Okay, now we want to find the modulus of that, and so we can again use what's given in the formula sheet to work that out, and we come up with that expression. And it's at this point that you could perhaps start to make use of your calculator. We'll look at that in a moment. I'll just work it through by hand. Finally, skipped a few steps there, but you would be able to square both sides. So you get 13x squared plus 117 over that is equal to 1 still, because 1 squared is 1. Simplify that, and we get down to x squared is equal to 4, which gives us x equals plus or minus 2. So there's our solution. So we can use some of the features of the calculator, but you have to be aware of what your calculator can and can't do for you. So we could use the numeric solve on the question as it was given. But the issue there is that if we do that, it will give us one solution, and you need to be aware that there could be other solutions and go looking for them, or at the point where you had the expression simplified, you'd done the division and so on, you could have put it in there, but the same result, we get a solution of x equals 2, and we have to still find that other one of x equals -2. And you should be aware of that, because when we go through this process, we're creating that squared term. We're going to have a quadratic. We should be thinking of 2 solutions and therefore go looking for it. Okay, so one final question to have a look at this time. We've got a polynomial in Z, and we're asked to find a quadratic factor given that Z equals I is a solution. So again, going to work it through basically by hand, and then look at some of the things that the calculator can do for us. Not going to work through fully by hand, but enough to give you an idea, and some of the additional questions that will be available on the website that have complete work solutions have these things fully mapped out for you. So given that Z equals I as a solution, then the conjugate, whoops, typo there, conjugate zero theorem says that Z equals negative I is also a solution. And so we've got Z plus I and Z minus I are factors of that expression. And hence, if we've got two linear factors, we can multiply them together and come up with a quadratic factor. But that's not the solution to the question, because in the fuller version of the question in the type document that you're able to download, the question asks for a quadratic factor in the form of Z squared plus BZ plus C or something to that effect. So that we have to go looking for the other quadratic factor, and that takes us into the use of polynomial division. So we've got this factor Z squared plus I and divide it into that expression, and we will get the required quadratic factor. So that's one approach. The other approach using the calculator is to get all of the linear solutions and then build up to quadratic factor. So we can use the C polyroots tool, which is in the complex numbers menu there, and C polyroots. So if I just point out, look at the calculations, numbers, complex numbers, tools. No, what have I done wrong? I don't want to do that. I wanted to go to algebra, not number. So calculations, algebra, whoops. Shouldn't have done that. I just need to get rid of that so that we don't. I've messed it up completely now. Let's just see if we can undo that. Bracket. I think that might have been what I had before. Can you give it to me? No, I've messed it up there now. Anyway, my apologies for that. Too heavy handed with the mouse clicking. So we will fix that up in a moment. And I've clicked on solve. That's why I have messed that up. Now that I can look at it, and if I do C polyroots and solve there, that's better. Okay, quick little fix up. So it gives me these solutions, and of course your calculator is going to give you an approximation, but on inspection with a little bit of existing knowledge, you'd recognize that as the square root of 2 and so on. So we get that these are the roots. Z is equal to negative I, 2 minus square root of 2I, and 2 plus the square root of 2I, which if we put it into factor form as factors, so Z minus I, Z plus I, and so forth, and then we recognize that these two multiplied together will give us this result, which is the solution to the question that was asked, to find the quadratic root in that form. So those are 3 quick questions on complex numbers. You'll find some additional problems on the website, and some of the earlier questions that we didn't look at in these webinar, you'll find some basic, straightforward, simple questions on the use of this C polyroots tool and so on. If you're not familiar with that, that can be quite useful for getting the complex roots to an expression there. So I think that is all for us. We have nothing else to say except to remind you again to make sure you take advantage of the tools or the resources, the worksheets and the solutions that will be available on the website. And having said that, I think we're finished. And on behalf of Stephen and myself, thank you very much for joining us today.